Okay, so now this is the third video, and we'll introduce the kind of building blocks, the multi-head attention, which is a building block of every transformer. We'll also talk about a variation of multi-head attention, which is a masked attention used mostly in text. And we'll talk about positional encoding, which we mentioned but haven't discussed thoroughly. So, um, this is so essentially a multi-head attention is kind of several single attention blocks as we presented them in the previous video. Let's remind ourselves what we had. So basically the input, we have a representation for each token. And then we have single attention heads. So what is an attention head? An attention head is just attention mechanism, basically defined by matrices. The core matrix WQ and the key matrix WK and the value matrix WV. And every attention head has a different such matrix, and all of them are trainable. So here in the image, you can see three such attention heads. And essentially, the input are the token embeddings, and the output are also an updated version, as we discussed, of the token embedding, which takes into account pairwise interaction. Now, notice that every attention head has its own output. So if here the input consists of a single embedding for each token, after the attention head, suddenly, if we have three heads, then now we have three representations for each token, each one defined or computed by the attention mechanism with three different matrices, WQ, WK, and WV. Okay, so once we apply the attention mechanism to the original embedding, as we say, we have, in this case, three embeddings for each token, and we would like to merge them back into one. So we get, like, eventually we get a single embedding for each token and not three. So the way to do that is just by concatenation. So we concatenate the updated embedding for each, that is the output of each head. So for each token, we have ZI1, ZI2, and ZI3. So this is, once we concatenate, it's a matrix of size D, which is the dimension of the embedding, times 3. And we merge them with a matrix WO to obtain, or it can be a vector, WO, which essentially gives us a single embedding for each, or a single embedding for each token. Okay, so if we look kind of like at all the tokens together, then we have WO as a matrix that kind of combines the different tokens. So we can think about it as kind of through, right, for each token we have three coefficients, right, that define how we concatenate the tokens, and the coefficients could be different for every token. So eventually WO, which merges the different the output of the three heads, is a matrix of size 3 over the number of tokens. Okay, and this is just a learnable linear layer to merge the output. Eventually, we get after the merging, we have the same dimensionality as the input. So we have like a new representation for each token. And this, as we said before, we use as input to a feed-forward network. So we have a kind of like a non-linearity applied to the new embedding, and this produces an output. And all this process is called a multi-head attention. And this is one of the building blocks of the transformer network. Now, what's the difference? So we have a multi-head attention. What is the masked multi-head attention? A masked multi-head attention. So this is used, for example, in text. In text, usually I train the network to produce the next word based on the current set of words. So once I produce like a part of a sentence, so this is used as an input to produce the next token or the next word. And to that end, in the training process, I would like so the input to the network during the training process is the full sentence, right? So each word is a token, but I would like the output to be dependent only on previous words, not on future words. Okay, so that basically means that in the attention mechanism, I change the um, correspondence or the weight matrix originally defined by a softmax function. I alter it to make sure that future words do not impact the new representation of current words. Okay, and this is the way to make sure that there is no such dependence because we want future words to depend only on previous words. So this is a masked multi-head attention. In the paper, it's just a regular softmax plus some element Mij. Mij is either zero. If it's zero, so it's the same softmax as before. This is if I is after J. Okay, so we can it can be taken into account. But if J is a future token, then we add minus infinity, basically making the coefficient Aij to be equal zero. Okay, and then make sure that it doesn't affect future tokens. Okay, so this is a mask multi-head attention. Okay, so again, think about again on the graph of tokens, the directed graph of tokens. Basically, the upper triangular matrix, okay, of the weights in the graph are zeroed out to make sure that only the time is preserved. Okay, so a token can affect a future token, but not one which is previous. Okay, so that is a masked multi-head attention. Lastly, we have, so this is an element we skipped before, so now we go back. We have the positional encoding. So until now, we talked about the tokenization, kind of like breaking up a sample into small parts and creating an embedding for each part, for each token. But if we don't add anything else to the embedding, then essentially a sentence becomes a bag of words because if we take, say, 5 words, you keep using that word and change the order randomly of the words, we get kind of the same input. And that is, of course, doesn't make sense. Okay, we want the order of the words to have meaning. And that is why we add an element that corresponds to the position. So here we had a couple of variations of what exactly do we do to represent word position. Originally, in the paper, attention all you need, in the first couple of years after that, it usually used kind of a fixed positional encoding. So essentially, we have the original embedding EI, and we add an element PI. PI is for positional, and PI is computed by some as a sine or cosine function, depend exactly on which element within PI we discussed. And the idea is that this added component is similar for locations that are close to one another, right? So sine position is similar to sine position plus 1. 8 times 10,000. Okay, so this is kind of a bit of a complicated functions, but the actual function itself doesn't really matter. The idea is to create some position representation that is, I would say, smooth. Okay, so two close positions have similar position representation. Another idea, which is, I think, more modern, is that the representation is not created by an additive component pi, but by some rotation matrix Ri. And here the main idea is that the difference between this operation for two position is a function of their distance. Okay, so it doesn't like if I look at the difference in this operation, it's fixed if I and j say are 1 and 4 or 2 and 5, right? We have like kind of the same effect of these rotations. So this is another interesting idea, more recently, kind of like the sinusoidal additive component. And lastly, in modern architectures, usually this is actually a trainable part, right? So this is if I take I can represent, say, a matrix P, which is a concatenation of all possible, say the maximal position is, say, 300. Okay, so this is L max. So I have a matrix of size D, which is the token dimension, and L max. And this is a trainable component. So I can actually kind of obtain something that is more flexible and might be more meaningful in terms of how it represents a position in a sentence, in an image, etc., etc. Okay. Now we mainly discussed the position encoding in a sentence, which is one dimensional, right? We have one direction in the sentence. In an image, it's usually two-dimensional. So it can be, for example, if we're looking at a trainable position encoding, so it can be two matrices, px plus py, so two additive components, etc., etc. So there's a lot of variation of this idea of position encoding and exactly how to represent it. Okay, so this basically, I think after this video, we kind of covered all the independent building blocks. We talked about tokenization. We talked about the representing each token individually. And we talked about the attention mechanism and the multi-head attention. In the next video, we'll talk about how do we add and combine all these interesting components together to get a really powerful network that can kind of, generate and do all the amazing things that we see a language model do.